So today what we're going to be chatting about is what's called magnitude of rotations and measures of arcs. Another way to consider it, instead of just talking about rotations, if we just talk about measures of angles. We're going to talk about effectively angles today. And we are going to look at three different units that we talk about. So three different units for measuring angles. One of them is called, one is called degrees, revolutions, and radians. You already know degrees. Hashtag, we figured that one out. Revolutions, you can figure out just by the word. And radians, you say WT Fadango. All right, so as we look at basic arithmetic, what are the pros and cons of using feet? Well, the first one is that it's irregular conversions. Miles are 5,280 feet. Inches are 12 inches in a foot, so it's irregular. But the pro of that is that 12, you can cut into quarters, into halves, and into thirds. Notice when I'm taking, a con of the metric is that 10 is only divisible by 2 and by 5. Which 2 is common, but 5 is not common. How often do you say, please may I have 1/5 of a pound of something, right? May I have 1/5 of the length of that rope? Most likely say, oh, I have a quarter. These are or a third. These are far more common than a fifth, okay? And in fact, over here, this one is also divisible by 6. Again, not as common, but it's an additional option there. The pro of metric is the tens, right? Everything is by tens. Centimeters means 100 or hundredth. So we count pretty much by tens, 10 to the 1, 10 to the 2, etc. So it's so much more easy to convert. Now, in the United States of America, another pro is that we already know the English system. So that's why it's familiar to us. So if I said, oh, we're going, I'm going to drive 2 clicks out from here, or 2 kilometers, you're like, oh, how far is that? Because we don't know the conversion so much. You personally might be, but most Americans probably don't know so much. So what we're going to look at today are the most common method, degrees, of measuring pretty much rotations or measuring angles. However, we're going to look at something more uncommon and yet logical, revolutions, and finally radians. And radians is the standard for most advanced math. Radians are the standard for most advanced math. In your calculator, whenever you see, or if you have a scientific calculator and you see a D or sometimes a deg up on the top or on the left, and the radians might say R or rad. So we're going to explain a little bit the difference between those two today. So by way of introduction, we're going to talk a little history, because the Babylonians are one of the biggest influences in our math. We use, you don't need to write this down, it's not, it's important in interest, but not important on a test. We have 60 seconds, right? We have 60 minutes, and of course, hopefully you've ever asked yourself, why is it 60 and not 100? Why is it 60 and not 12? Well, like I said, it's the same reason that we use 12 inches, because it's easy to divide. Again, Babylonians said, well, they actually had something called, I think it was a hexadecimal system. So they use 60s a lot in things. And so the influence of the Babylonians is extremely important to us because of the 60 itself. So we have used 360 degrees to talk about one complete revolution around the circle. To go all the way around the circle, we said 360 degrees. Well, again, why might we like 360 degrees? Well, because we can cut it in half easily to be 180. We could cut it into fourths to be 90 degrees. And we can even cut it again in eighths, right? But not only that, I could have taken the whole thing and cut it into thirds, like this, and each one of those be 120. But then I can cut the thirds in half as well to get 60 degrees, like so. So we've got lots of factors. We can divide that number into a lot of ways, 1/6, 1/8, 1/10. The only thing we can't do is 1/7. Can we do 1/9? Well, also. But on the top 10, these are the only two excluded, 1/7 and 1/9. But if I had 100 degrees, what if I had 100? What if the 100 degrees was all the way around? Yay, I can do 50. Yay, I can do 25. Now you're stuck. Because now you're in decimal to get to here. Oh, well, let's go the other way. Let's go into thirds. And you say, 33.3. Oh, snap, we're already into decimals. And dividing by 3 is one of the most common things in the history of the universe. All right, so Babylonians actually used common sense when they did it. And they weren't thinking about massive calculations with 1,000 degrees or whatever. So that's the idea behind 360 degrees. It's just like we use 12 inches. Okay, so let's talk a little bit about the basic idea of rotations and angles, etc. So first off, y'all know what a circle is. So first off, a circle, it's the set of all points on a plane that are a fixed distance from a point. And of course, we call that the radius, right? So, if I had, and the red here describes that, if I have this distance right here, for now we'll call it R, and we just spun around, it would be all these points all the way around that's equidistant from Q. And notice we're staying on the plane, so I'm not going above. If you did go above and around, you would get a sphere. So we're just talking two-dimensionally here. So a rotation, therefore, a rotation is a transformation that pretty much, and notice I put the word slides in quotation marks because I'm not sliding in straight lines. It just slides the point along the circle. So A slides along the circle to be here. So that would be your rotation. So we're going to be talking pretty much about rotation, and when things rotate, we end up officially as A rotates here to B, so A maps itself to B. Notice what's formed. What's formed is an angle based on the rotation here. A couple things we want to point out. This here is called the center of rotation. Oftentimes, you'll see it as an O, but not always. Another super important thing is that this angle is often going to be called a Greek letter. One of our first Greek letters, besides pi. This is read theta. Alpha, beta, gamma, delta, etc. But theta is in there, and theta is pronounced with a TH. So, and another thing is this one's ironic, but positive is counterclockwise. Hence, negative is clockwise. So if I say theta is 50 degrees, I'm saying 50 degrees in the counterclockwise direction. If you're British, you would say anti-clockwise. Quick change, 360 is divisible by 9. The only one it's not divisible by is 7. So why not choose a number, multiply this by 7? Why not use that one? So that all the first 10 numbers work into dividing it. So it's fairly arbitrary. So mathematicians have come up with other ways to describe besides degrees. So the next one we're going to look at is called revolutions. Bang, bang, it's a revolution. All right, first off, a revolution is just all the way around, right? So a full turn. So if this is my point here, and here's A, and a full turn, to there.
That was a pretty good circle.
Yeah, like,
is 300 to the end, right? All right, so 360 degrees is a full turn, also known as one revolution. So it maps to itself. Of course, a half turn. And if here's A, so I'm going to put A prime right here. And clearly we see that a half turn is 180 degrees. And we would call that a half revolution. And we can say rev for short. Again, notice I'm going in the positive direction by going anti-clockwise. Oh, behave. Next, if A were to go quarter turn, to there, A prime, we would call that puppy a 90 degree in the positive direction or quarter revolution. Let's take a moment to convert revolutions. So we know that, and here's our basic idea, is 1 revolution is 360. So clearly, remember the key, folks, is to do something called unit. When you convert units, you need to have the units doing reduction to reduce each other. So I'm going to put the degrees down here and the revolution on the top. I could have done the reciprocal if I wanted to cancel out the revolutions. So now the key thing here is that my degrees drop out. So the unit cancellation, the only unit left is revolution. So I know my answer will be a revolution. I do not, folks, I do not have to use 1 and 36. I can use anything. I could have used 180 and 1/2. I would just put 180 there and 1/2 there. The issue is that it just ends up being more work or less work depending on which conversion factor. All right, so effectively all we're doing is taking 720 and dividing by 360, so the answer is 2 revolutions. Now notice that 2 revolutions ends you in the same spot, right? Here, so if I'm there, takes you again, takes me back. So in terms of position, there's no change. I'm still in the same spot. But the revolution tells me that I've done it a couple times. So I'm more dizzy here than I would be on a 360. So in chatting about radians, it's a new, notice the root word there is radius. Radians are based on a radius because what is the definition of a circle? We've already talked about a definition of a circle. We have a point. We have a distance away from that point, so that's the distance there. And then we just loop it around, go all the way around, and that is every single one of those points, not the inside. So we're not talking about the region inside. We're just talking about the fence that goes around. That here is my circle, and it's always defined by R. Radius is defined by R. By the way, this is why some people do not like pi. Pi is 3.14, etc. And it is based on, do you guys know how to calculate pi? Where it comes from? Your circumference, we know is, so pi would be circumference divided by the diameter, or another thing to say is circumference divided by 2 pi. So some people actually say, well, since a circle is defined by R, then maybe pi should be defined by R, not by D, D being diameter. So some people actually make the case for tau, which is 6.28. Instead of saying C divided by, they should say C divided by tau. And then you have, because clearly 2 pi is going to be tau. Anyways, all that to be said is, instead of saying pi as our special number should be tau. But I digress. So, based on radians, is based on radius here. And again, so let's see how it argues. So notice that if I had a degree here for the distance from G to C could be some degree. We'll just arbitrarily call it 30 degrees, right? So this is 30 degrees. Well, so is this. This is 30 degrees as well. The problem is, clearly the ES arc is clearly larger than the measure of that. Is there a way to communicate that there is something larger and not simply just saying, oh, that's 30 degrees, that's 30 degrees? All right, so that's the idea. That's the conundrum that's dealt with. So here's what they came up with. So let's chat first. Degrees and revolutions can tell us about the size of the angle, but nothing about the distance or the piece of the circle or the piece of the circumference. So here's what a radian is. A radian is this. If I have a radius of a circle, a radian says, take that radius and wrap it around the circle. So if I start wrapping this around the circle, I get one of them there. Then I get another one here. Then I get another one there, and another one there, another one there, another one there, and then there's a little bit left over. So a radian is the radius wrapped around a circle. So notice in terms of the large circle, this is my large radius. And if I were to start wrapping it around the circle, it would go to about here, and then go to about here, go to about there, go to about there, etc. So I'm just wrapping the radius around the circle with a little bit left over right there. So you can almost wrap a radius 6 times around, and it doesn't matter which circle you're talking about. This radius right here wraps a little bit more than 6 times around. This radius here wraps a little bit more than 6 times around on the larger circle. So that's what it means. That's what a radian is. A radian is not a degree. A radian is kind of like saying the distance around the circle, or kind of like circumference. So a common conversion is this. We know that circumference is 2 pi r. We know that circumference is 2 pi r. So that's effectively what radians will be. And we often will define a radian in terms of pi because it is going to be talking about the distance around, as we see here, based on pi. Now, oftentimes, we're also going to be assuming something about r for now. R usually is 1, and we call that part of the unit circle. We call it a unit because it's just 1. Just 1. The radius is 1. But the radius can be anything at once. But for now, we're just calling it 1. And so the circumference around that would be 2 pi. That would be the distance all the way around. So a common conversion would be something like this. 1 revolution is equal to 360 degrees, which is equal to 2 pi radians. All right, so continuing on, if I did half a revolution, that's 180 degrees, which is just pi radians. So take a moment here, to the best of your ability, and start filling out this table in degrees, radians, and revolutions. And order doesn't matter, and if you leave stuff blank for now, totally fine. As we start filling this one in, of course, this one's the easiest, and then cut everything in half for this. Now again, all we have to do here is cut in half again, or cut in fourth from the original. So now this one, instead of saying pi, it's going to be pi over 2. Next up, revolutions we cut in half again, so that's 1/4 of a revolution. And for the most part, let's try to keep fractions where they are. Okay, so let's see here. Notice that pi over 2 cut in half is pi over 4. So that means 90 divided by 2 is 45 degrees, which means I'm going to cut the revolution in half as well to get 1/8 there. As we're reasoning through this, 1/4 plus 1/8, this is 2/8, plus 1/8 is 3/8, which means 45 plus 90 is 135 right there, which means pi over 4 plus pi over 2. Again, if we need to see how that works, plus 2 pi over 4. So now that gives me 3 pi over 4 to go right there. If this is pi and this is pi over 3, then 180 divided by 3 gives me there. So this is a 60 degree, also known as the angle on an equilateral triangle. So again, if I take this and divide by 3, I get 1/6. And other things to consider, 60 doubled is 120. So if you double the pi over 3, you get 2 pi over 3. And then when we double 1/6, we get 1/3 of a revolution there. Notice that 120 plus 30 is going to be 150, so we can get to there in just a minute. But if we took this and divided by 12, we would get to there. So take this and divide by 12 to get pi over 6. Again, 2 pi divided by 12 will get you pi over 6. And then just take this and divide by 12 to get 1/12. 0 radians and 0 revolutions on that one. And notice I could just take I can just take 30 and multiply by 5 to get to there. So take this and multiply by 5. So 5 pi over 6 and 5/12 there. Now this is going to be something you will want to memorize. So let's take a minute now to convert 1,000 degrees to radians exactly. So exactly means we're probably going to write it like a fraction in terms of pi. Approximately means we just plug that into our calculator. 5 times pi divided by 6 to get a decimal of sorts. All right, so 1,000 degrees. So remember how we convert. That's 1,000 degrees over 1. And we know that 360 degrees is equal to 2 pi. We know that pi is over 180. So if I said pi radians over 180 degrees, so we're doing our unit cancellation. Degrees will cancel out right there. Again, I can divide by 10 on each one of those. And notice what I have now. 100 is even and 18 is even there. So I can divide this by 2 to get 50, divide this by 2 to get 9, and neither of these are divisible by the same factor. Again, that's called relatively prime, when two numbers have no common factor except 1. So the answer would be this, 50 pi over 9, and our unit is radians. Now to do an approximate value there, all we have to do is plug this into our handy-dandy calculator, 50 times pi divided by 9. And part B, when we convert it to radians, so there's my A. Part B is 1,000 degrees, converts to approximately 17.45 radians. It doesn't say where to round it, so hundredths or tenths is going to be reasonable. Let's take a gander at example number 3 here to see some application, and especially in terms of radians, how radians are applied. So this will argue the case for radians, and then we'll use the formula in a moment. So finding the length of an arc. So what's the length of an arc? So if we have a circle and the central angle here is 50 degrees, like so, we want to know how big this arc is. So if you walked the distance from here to here about the circle, but only go 50 degrees, how far did you travel? Well, the only other thing we need to label on this is that this is 6 feet right here. So, how to approach it? Well, there's a couple different ways to approach it, but let's just consider, notice that this question ultimately is asking, how many radiuses is this right here? Or, better question, how many radians is this? So, let's just consider it, for now I'm going to consider it as a proportion. This is 50 degrees out of 360 degrees is equal to the unknown amount over the total amount. And of course, we know the total amount is 2 times pi times r, because that's your circumference. Circumference is 2 pi r. Of course, that looks familiar, 2 pi being 1 radian. So I can just plug that down here, 2 times pi times 6. That'll give you the circumference. The part over the whole is equal to the part over the whole is what we're doing on this. Before I even start cross multiplying, I'm going to go ahead and reduce what I can. Degrees drop out and the zeros drop out. So now I can multiply and divide. So I didn't bother multiplying it out because I'm going to go ahead and start reducing things as I can, like so. So my exact answer is this. X is 5 pi over 3. But again, since this is a question in the real world, we should probably bring it back into the real world about how far it is. So now we just need to divide and multiply here. 5.2 feet. 5.2 feet. In other words, it's less than 1 radian. The circle arc length formula states that if S is the length of an arc of a central angle, so here's my central angle, and the arc is this part here, so that's your S there. And the central angle has theta radians in the circle of radius of r with radius, of circle of radius r. Then this length right here is just theta times r. That's it. Theta times r, but of course it has to be in radians. So the benefit of this is that radians help us find really quickly, help us find how long or how far we travel along the circle there. Example 4, a swing hangs from chains that are 8 feet long. Like so. So how far does the seat of the swing travel if it moves through an angle of 1.25 radians? So it swings this way and it swings this way, which means that this angle right here, theta, is equal to 1.25 radians. Well, we already know that this arc length here is called S. I prefer not to use S because my 5s tend to look like that, but we'll stick with S for now. So S is equal to, simply put, theta times R. That's it. So theta is 1.25 radians, and my R is 8. And so now we get the answer to be 12 feet. So when swinging 12 feet back and forth, not straight across, folks. We're not saying straight across. We're saying the actual distance traveled around the piece of the circle, 12 feet.